Mankind has had many different ages through which it has used certain materials to help aid its development. For example, we've had the Bronze Age, we've had the Stone Age, we've had the Iron Age, and it's true to say that in today's world we're in the polymer age. I mean, you can't go 5 seconds without seeing polymers somewhere. If it's something made from polymers, kept in polymers, wrapped in polymers, eating polymers, you know, they're everywhere. In fact, you just look around you can see a variety of polymers, and I bet there's hundreds of them that I can find in this house. Let's have a look.
They used to make LCD television and computer screens.
You use them to make smartphones? Yeah, I know. Tell me about it.
They used to make really comfy fabrics.
They used to make skin-tight sportswear, make trampolines. Even in the garden, plant pots, garden hose, both made of polymers.
And the kitchen is quite literally overflowing with polymers. Before I go any further, I should really tell you what polymers are. Polymers are long chain molecules that are built up of continuous sets of repeat units, and these repeat units can be taken and broken down into what are called monomers, and these monomers are the building blocks of polymers. For example, say you've got monomer A, lots of monomer A, you want to put them all together to make a polymer of a continuous stream of repeat units of A, and this can go on for hundreds and thousands of times to make one long chain polymer. One real life polymer is made up from lots of chloroethene, which is shown here. I've got 3 molecules of chloroethene. Keeping the carbons together is a double bond, shown by these 2 lines, and if you break these double bonds, you can open up the molecule so it can form bonds with other carbons nearby, and therefore you get a long chain of repeating molecules. And this can happen again and again and again once you add more and more chloroethene, and you get this very long molecule with a repeat unit that looks like that. It's called polyvinyl chloride. It's got all sorts of applications, and the number of repeat units is represented by the letter N, which can be any number from 10 to 100,000. It's a huge number of repeat units that make up these long chain polymers. And polymers, based on the way that they're designed and made, can be used for any number of applications. But plastics are very commonly used for food and drink packaging. Just a quick look in the fridge and I could see lots of items that were kept in plastic packaging. I just took a few examples. There's this drinks bottle made of plastic, sandwich filling or ham that's kept in plastic, and that's the same as a lot of items in the fridge that just want to be kept free of moisture so that they last longer. And of course, milk these days comes in plastic packaging. One of the most common plastic packaging is polyethylene or polyethylene. It's got a repeat unit, a repeating structure that looks a bit like this. It's one of the most simple to make polymers and very commonly used. This is how it's made. The first step is the initiation. You start off with a carbon-based molecule which contains a peroxide bridge, which is where you've got 2 oxygen molecules bonded together. Now a covalent bond, is just a pair of electrons that are keeping the 2 atoms together. However, in most cases, if we want to break this bond, the electrons will travel together and you get one negatively charged side of the molecule where the electrons have moved to, and one positively charged side of the molecule where the electrons are vacated. However, in this case we want to add some UV radiation or some heat which causes the bond to break in a slightly different way. In this instance, the electrons will be shared on either side of the molecule, which is shown by these fish-hooked arrows, which represents the movement of 1 electron. Now, this forms 2 molecules which have 1 lone electron. Now, these are called radicals, and radicals are very unstable molecules, very reactive molecules. And basically, if we put a radical molecule near one of the ethene monomers, which contains a double bond, which is quite reactive itself, basically this radical will move to attack here, and then one of the bonds in the carbon-to-carbon double bond will break in the same radicalized way. And then you've got the movement of one of the electrons to make a bond with the other radical, with the peroxide radical, and then the other one will move on to the other carbon to form another radical, which we can see here. This is basically a continuation of the first initial step. So in as much as in the first step you had the radical which attacked the double bond, in the same way the carbon radical, which was made in the initiation, will attack the double bond in exactly the same way. So the double bond will split into two. One of the electrons in the bond will go and make a bond with the carbon radical, which will form this bond here, and the other electron will move to this carbon and form a radical molecule here.
Once the propagation
now this step will happen over and over again each time
you
it
end up
encounters
with a
a
huge
new
radical
ethene
molecule with X number of repeat units. That'd be
hundreds of thousands of repeat units maybe. At some point you want this to stop because you want to get a complete polymer and you don't want the radical to continue reacting in that way. So the best way to do that is to take another one of these long radical polymer chains, and basically you put the two together, and the lone electrons on each radical will attack one another and form a bond which brings these two together, and you end up with a very long complete polymer chain with X plus Y repeat units with the end group on either side of the molecule, so you end up with a very stable polymer, polyethene. Polyethene is so useful because of the way the chains pack so tightly together. Because it's a very long, thin molecule, being a polymer with no side branches, the chains can get very close together, and any intermolecular forces are intensified by the proximity. Therefore, it's very strong and keeps out moisture. This is very useful when you want to be storing things like milk or
but there's two major problems
quite
with
easily.
using
You keep out the moisture, they don't go off, and also you want it to be able to contain what it's got inside of it without
they're
it falling
synthesized
apart.
using ethene from crude oil,
Which is a very finite resource. You know, we've got a limited amount of it, and with problems in the Middle East, which is where a lot of the oil comes from, we might actually be running out of oil a lot sooner than we think. Despite the fact that a lot of people are putting a lot of effort into making sure that we use less polymers, we use less plastic packaging, and that we recycle what plastic packaging we use, a lot of plastic isn't recyclable, and also a lot of the plastic that is recyclable ends up in landfills anyway. So we've got to start thinking of alternative ways of packing food. You know, we could go back to the way we used to do things. For example, we used to use glass to store a lot of things. You know, a lot of people still get milk in glass bottles. The only problem with glass is that although it does a very good job at keeping out moisture and it is very strong, it's a lot heavier than plastic, which means that you can't get quite as much in one truckload when it's transported, so it costs more to transport. And also, it requires a lot of high intensity heat to actually form the glass like paper, which is used to hold some much more expensive than polymerization of ethene, which is done at 60 degrees Celsius,
and it's not very good at keeping moisture out.
So as far as non-plastic forms of packaging are concerned, there's not a lot of good cheap options. So we've got to start thinking of ideas that involve plastics, but ones that don't last hundreds of thousands of years in landfills. Acid.
Is a fantastic polymer to use for plastics because
the monomers it's made from, lactic acid, comes from natural sources such as cornstarch, and it can also biodegrade back into the lactic acid, which is a harmless substance on the landfill conditions when it's in the landfill. It does this when water attacks it, attacks the ester bond, which is shown in this highlighted region here, and it cleaves this bond between carbon and oxygen, adding an OH group to this carbon. And it forms a smaller lactic acid as a result of this side,
polymers,
and a lactic acid molecule which is completely harmless on this side. And this happens over and over again until you've got all lactic acid and no harmful polymers.
So if we all use biodegradable polymers more often, the price should go down, and I can think of no reason why they shouldn't be used over crude oil based polymers.